All right, hello and welcome. In this video, we're going to look at how to calculate the time constant of an RL series circuit. So the first thing we need to do is build up our circuit. We've got a couple of component values here, so we're going to grab those out. So we'll right click, place component. From here, we'll go to the drop down for groups and select basic. And we want to look for a 6K resistor, so we can just grab a resistor of any type and pull it out, and we can adjust the value of it in a minute. We also want an inductor, so we'll go down to inductors and pull one of those out. Control R allows us to rotate it sideways. Place that in. We also need a voltage source. There's two options for voltage sources. We can use the function generator over on the sidebar, second one down, and that allows us to put in a square wave with the duty cycle and a frequency. Or we can use a power source. So we'll go up here into sources, grab signal voltage sources, and select the clock voltage here. Okay, that out, and that's a square waveform. So now we just need a ground. So we'll go to power sources and grab out our ground and place that ground in our circuit. And then we're ready to connect the circuit. We know this is going to be a series connection, so we'll go from our voltage to our resistor to our inductor, and our inductor back to our voltage supply. And after that, just connect our ground to that bottom wire, our negative side of that voltage. And from here, we're going to calculate our time constant, and we're going to use the measured voltage drop across the inductor and the measured voltage drop across the resistor to determine if that time constant is accurate. So our time constant is based on our inductor and our resistor in the circuit. So we need to update those to be the correct value. So we'll double click on the resistor. We want it to be 6,000. So we'll say 6K. Okay, that out. And then our inductor as well, double click on that. We want that to be 160 millihenries. So we'll update that. Okay. And our voltage source has a lower frequency than 1,000. So it's going to be 250 hertz here. Make sure you put your correct values in for these. We see the duty cycle is already set to 50, and we have a 5-volt magnitude there, so we're okay with that. So from here, we can use these two values to calculate the time constant that is expected for this circuit, and then we'll measure it, and we'll see if it's accurate. So in our calculator over here, we can say that the time constant for this is going to be the inductor divided by the resistor. And watch out for the notation here. So we have our inductor of 160 millihenries, so times 10 to the negative 3. And we'll close that off and divide it by our 6,000 ohms for our resistor. So 6,000, that's 6 kilo ohms there. We are given a to the negative 5 value, and so we want to move that back. We've got 2.666 or 2.667, and we want to make this up to a negative 6. We're just going to move this decimal point back one space between these two sixes here, and we'll have a 26.67. And so that is what we are going to place into our calculated time value. So that is our time constant. So 26.67. It's times 10 to the negative 6 now that we moved that decimal point back by one location. And so we can say that that's actually just a micro. And since this is a time constant, it's going to be in seconds. So 26.67 microseconds is the time constant we expect for this circuit. And I give you the time constant chart over here. So this chart tells us that we have one time constant that should give us a full magnitude of voltage across our resistor, right, of 63.2% of the total voltage. At the second time constant, that's after two intervals of 26.67 microseconds. That's going to give us 86.5% of the total voltage dropped across that resistor, right? It's specifically talking about the voltage across the resistor up here. And so that means that when we're looking for the voltage across the inductor, we need to flip this percentage over, because if 63% drops across this resistor, then the other percentage, whatever that is going to drop across this inductor, VL. Right? So we need to be able to account for that. We know 100% comes from this device here, so we can just subtract that out. We can say, well, if we want to know what our inductor is doing in terms of that, we can say that we have 100% total voltage. We subtract what we know that resistor gets at that first time constant, 63.2, and we're left with 36.8%. So we expect this inductor over here to have 36.8% of the voltage total, right? That voltage total is 5 volts. And so we know that 63% of 5 volts goes here and 36% of 5 volts goes here for our first time constant. So that's what we're going to calculate out here. So let's get rid of some of this here. And we'll do that. So the first thing we need to do is figure out what our voltage drop across that inductor is, and then we can figure out what 36% of that looks like. So let's use our oscilloscope, pull that out. That can be found on the sidebar over here, the fourth one down, or you can go into your Simulate tab and select Instruments, And then that's also the fourth one down there, oscilloscope. It's going to give us a 2-channel oscilloscope. We place that out in the field here. We want to measure across both of these two components. We want both of them down here, so VL and VR. So we can place the first one around this resistor and just place the positive in front of the resistor, the negative on the back side of the resistor. And the positive of the B channel can go in front of the inductor and the negative on the back side of the inductor. And we want to change one of these colors. The positive lead of either one of them can be changed to adjust the color in the oscilloscope. So we'll click on one, make those blue dots appear, and then right click and do segment color and select any other color so that we can see the difference on our oscilloscope there. Okay, so we'll double click on the oscilloscope, and this gives us a time interval in terms of voltage. So it's going to only show us the voltage that we get, not the current, but we can always determine the current if we know what the voltage drop is. Okay, so that gives us a really, really small signal. So we're going to zoom in. So this zoom in is on the time base here. It's going to stretch it horizontally. And so we can just zoom in until we see a nice clean signal. And we actually want to zoom in pretty far on this because we want to see the top and bottom intervals. And we actually want to stop it right here, and we'll zoom back until we find that upper interval. Because there's two sides of this. There's a rising and a falling edge. There it is. All right, so that's what we're looking for. 20 microseconds got me there, but it might be a little bit different on yours. We can also stretch the upper rise on this one by changing the voltage scale over here. So click over here, we've got that 5 volts. We can go down one, and that's going to stretch it up a little bit higher, and that gives us just a little bit more view on that. Okay, so we see these are almost inverted of each other, right? We have this blue one that comes up and falls down, and then we've got this red one that waits a minute and then slowly rises up. And if we were to flip these over and overlay them on top of each other, we might end up with just a nice little square waveform, right? Where the blue one rises up to the top. And if we were to flip that red one upside down so that it laid on top of the blue one, it would have a flat top across the top, and that would give us this peak, this square waveform. So we know that the total voltage is here, right? Some of it is across the inductor early on, and some of it is across the resistor later. And that's what we see here. We see that the voltage across the resistor is really high later, and the voltage across the inductor is really high early on. And so that's what we're trying to characterize here. We're trying to characterize the slope of the blue line here and the slope of the red line moving up, because we can find our time constant from either one. Let's write our time constant back down here. We know that it was 26.67 microseconds. And so now that we have the voltage, we can, or now that we have seen the voltage on the oscilloscope, we can measure it using our meters here. So we pull these two out. We're given 2 of them. If you click on them, you see this triangle gets bigger on one. You click on the other one, the triangle gets bigger on the other one. So when we pull this out, we see that it actually follows the red line right now, and we actually want it to follow the inductor because we're trying to measure the voltage drop across the inductor, and we know that we made the inductor the blue line. And so we can double click on the blue line, and that's going to transfer that dot here to the blue line. So double clicking on the red line puts it back, or you can right click, select trace, and go to channel B on your trace line. And that's going to do the same thing. So from here, we want to measure the beginning, the very, very start of the signal. And so we can go all the way back here, right click on this blue line and go to next Y max. And that's going to send us to the very, very peak of that signal. And when we look down on our T2 channel, that's down here at the bottom, we can see that we can follow that across all the way to channel B, and we get 5 volts. Right, so that peak is at 5 volts. Now we need to find our time constant. And so that's going to be at 36.8% of our total peak volts. We know the peak volt starts at 5. And so we'll do that. We'll say we have 5 volts, and we can multiply that by a percentage. Watch out for this. We've got to move that decimal point down. Percentage of 0.368. Right, and that gives us 100 or 1.84 volts. And so we're going to move the T2 here to 1.84 volts on this sloped line here. And when we move it up here, we see that T2 reads right here. And so that's at 4.65 volts right now. It's at 4.65 right now. So when we click on this and move it, we see that that goes closer and closer and closer. It's really hard to get it exactly at the value you want. So you can right click on that probe line and tell it to set forward to the next Y value. And then here we can type in our 1.84. Well, okay, that. And it jumps down there, right? And look at this. It is exactly what we expected it to be, because we know that this is our time constant, 26.67 micro, and that this is the time constant that it just gave us there. The distance between these two is this 26.67 micro. It's our first time constant, right? And we see that there's other time constants over here, so we might scoot up another 26.67 microseconds on our x-axis over here and see the next time constant as well, and you can calculate that out, right? Because you know that's going to be that 86.5 for the second time constant minus that 100, and that's going to get you that side for the inductor. So that is what we want to write down over here. We want to say that we got 26.494 microseconds. You might even take a screenshot of this to show off your equations here. Now we can reset this and go after the red one. So we know that the signal kind of starts in the same exact spot, right? That's where that red line also increased at. And so we can click on here and see that when we move our T1 forward, we can look at channel A, and we can see that that's when it starts to increase right here, 77.46. We go back, it's at a microvolt. Right? It immediately jumps up to millivolt right there. So we know that's the beginning. We go down, we are at the negative, we're at that FV, the femtovolt. So that right there is where we want to start at. The second cursor here is going to go on the red line. So now we need to double click on the red line or right click, select trace, and select our channel A again. And that's going to be our voltage across that resistor, right? Because that's the red probe line right here leading into channel A. So now we need to calculate what that voltage should be. We see it following that red line all the way up, and we want to figure out where that time constant is, and it should be right about the same time constant that it previously was there. But this time, we now see that we don't have our maximum voltage yet. We need to go all the way to the end until we get our maximum voltage, and we might even have to scroll out a little bit. So now we see that T2 has a 5 volt right here. That's what we're looking for. That's our maximum voltage. So we'll keep our 5 volts, and we will multiply that by our first time constant, the actual time constant, and that's going to be 63.2 because we're talking about the resistor right now. Oops, we got to move that into decimal range, though. 0.632. That gives us 3.16. So when we scroll back over to our interaction here, we can move this thing backwards until that value, or forwards, right? We can start at the beginning and tell it to move forward. So set Y value moving forward, and we'll replace this with 3.16 and okay that. Right, you see this time constant down here also. This time constant is comparing the first marker to the second marker. So if you don't have your first marker in the right spot, it's not going to work. And so you might have to adjust that T1, T2 back and forth to try and get this to even out. But that's what we're looking for. Right, we see that no matter what, if we measure from the voltage side or from the inductor side, we still get that 26.457 microseconds, which is pretty darn close. It's really, really close to what we expect, give or take a little bit of tolerance maybe. Okay, let us know if you guys have any questions.